Hello, hello, hello. Mic check 1 2 1 2. Testing. Hello, hello, hello. Mic check one. All right, we sound to be all right and ready to go. Okay, what's up, world? We're back at it again, trying to conquer physics, and we are working on problem 2, section 1.2, which is kinematics. And today's problem statement states a satellite of mass m is in geosynchronous orbit around Earth. So let's just write that real quick. So we got a little Earth, mass big ME. We got a little satellite orbiting it, right? We draw a little cute. This has mass m, right? And then it says if the Earth has angular rotational velocity omega, what is the radius of geosynchronous orbits? Oh, okay, so that's interesting. So synchronous. At first I was like, well, what the heck does that mean? That means that if you got a mountain up here, pointing to the satellite, as Earth rotates, right, with speed omega, this satellite, Earth will be, time fast forward time. We got Earth over here, the mountain's pointing there. The satellite's gonna be over here, you know? I believe that's what that means. We could double check, but we're just gonna go with it and see what happens. And so this question, what does it say? If the Earth has angular rotational velocity omega, what is the geosynchronous orbit? I almost don't feel like we have enough information, but we're gonna play around with it. So the answers we have, I'll just write them down. Potential answers: G big M little e over omega squared, B G M little m omega squared, C G big M e divided by omega squared. But all this is to the 1/3 power D, the square roots of GME over omega squared, or E. There is no possible geosynchronous orbit. Does not exist. Okay, so our mission, find out what's the geosynchronous orbit around. And so let's see if we can figure something out. Okay, so if it says is in geosynchronous, it's kind of weird the way it's prefaced because it says that the satellite is in geosynchronous orbit with the Earth. And then one of the responses is like there is no geosynchronous orbit, which kind of tells us that it's trying. Doesn't mean it is. And so we really got to think hard about this one because I'm actually a little stumped. I'd hate to try to look for clues and examples, but we're going to try to give this a go, right? Because we're going to use a basic first principles. But if we have to use help, there's no shame in that. We'll go look for help, right? Okay, so we know the radius of this. I guess that's what they want us to find out, right? The problem says, what is the radius of the geosynchronous orbit? Okay. So I guess if it can be in geosynchronous orbit, there is a radius, and this is what we want to find out. So there are some equations that can be thrown out, like just right away, just to try to figure this out. If you have something following a certain rotational frequency or velocity, then it should follow the same. So one thing that we could know is that if this Earth has a rotational velocity omega, the units of this is basically degrees or radians per unit time, right? So that's what the units are of this omega. Or you could think of it as like degrees. So as this thing will rotate, let's say if it rotates well, I guess you could say it's Earth's rotation is 24 hours, right? Then this satellite's rotation should be 24 hours as well. Like one full revolution per 24 hours. So I have to match. And so from our satellite perspective, we know it has to go around. And in order for something to go around at this radius r at omega angular velocity, we could actually find out what its velocity is at this edge, right? I don't know if it'll be useful right now, but I have a hunch it will be. And so I believe the velocity will be omega times r, or r times omega. Cool, so we just have an equation. We'll probably need this, right? One thing we'd like to find out is if this is in geosynchronous orbit. I think we're also going to assume that it's a circular orbit, because in some cases orbits can be elliptical, but in this one I don't believe it is. I think it's circular. And so there is an equation of a force and acceleration needed to follow a circle. We might go into the derivation if needed, but I believe that the force or acceleration inward is proportional to the acceleration. The acceleration is equal to v squared over r. I believe that's what it is. And here we have an equation for v that we could plug in. And in this case, it's r omega squared. And this r is basically this r that it's tethered to, right? And so when we end up solving for this acceleration is equal to um, r squared times omega squared over r, which is equal to r times omega squared, because this cancels with that. And so we have an acceleration. Boom. This acceleration is dependent on this. But our job is not done because we gotta find out an acceleration, right? Well, what's the force? Let's just think of what's the force being pulled from here to here. Well, we could say it's Earth's gravitational force. And we can't just use a little constant g. We actually have to now use the force equation for gravity. And in this case, you can see it plastered all here, this g constant. And it's times the mass of the Earth pulling on the mass of the satellite over r squared. And this equation is n. So the force is being applied to this little satellite, so it's m little a. One thing to note is we have a right here, we have a right here, so we're gonna have to plug this a here. But right away we can cancel these m's, and so we have a is equal to g big M over r squared, and we say this a is also equal to r omega squared. And what are we looking for? We're trying to solve, so now we basically just want to look at these equations. We're going to solve for r, which means we're going to multiply both sides by r squared and move this omega over. So now we're going to have r cubed is equal to g m me over omega squared. And then we take the cube root of this, and we get r is equal to the cube root of g m e over omega squared. And do we have anything like that? Boom! Right here. The answer is C. Coolio, cool beans. Just in case cube root of something, it's the same as 1 over to the 1/3 power. So this is the same as g big M little e omega squared 1/3, which is C. Boom, boom. Yay. That was a pretty neat problem. I wasn't sure. So I guess, and this probably would be more helpful. It's like, what was the insight? So usually you want to look for equations that deal with factors that you have. So one factor that we had was this omega, right? We're talking about rotational things. And so usually there's some type of radius tethered. And in this case, we have a satellite orbiting Earth. So you know you're going to use gravity. So the important equations we needed right here, the gravitational equation, and then we also needed this equation, which deals with accelerations with constant velocity. So it's like a centripetal force, a centripetal acceleration. So we needed this, and there was one more thing we needed to know. It was the velocity part right here. We needed to know that when you're looking at a velocity of a point of something with angular velocity, it's the radius times the angular velocity is equal to velocity. Yep. So these three equations is what you needed to pull out in this problem. And so over time and working on problems, you find out what's kind of needed. Even in the beginning of this, there's examples and they kind of give you the equations. But over time, you'll develop this. And what I mean by over time is working on problems. So working on problems like this will help you along the way. And I hope this was helpful. In the future, we might try to go more in depth into this as I get better at explaining some of this. And as I actually build a community, we will be able to work on this together. And hopefully I can interact with you all more. In the meantime, toodaloos and keep shining. All right, keep learning. We need more scientists out there. That means you. All right, you do you, boo boo. Let's get it. Bye bye.